Welcome back. So this is going to be another one of sample section 3 walkthrough videos where I go through a bunch of questions. What I'm going to do though is now start to stagger it a little bit. I mentioned in another video that it's starting to get a little bit maybe confusing or a bit overwhelming, I should say, for people that are new to GAMSAT and are looking for practice material outside of the ASA stuff. So this is still going to be a walkthrough question. It should be helpful for everybody, but it's kind of an intermediate level this time. Rather than going for the really difficult ones, most of the ones that I put in the sample walkthroughs are maybe on the trickier end to really start preparing people for the test. But given it's a long way away and a lot of people are early in their study and maybe sitting it for the first time, and some people are just coming off of a lot of the crash course series that I do and looking to start applying some of the techniques, I figured we'd go through some sample questions that I write that are somewhere in between the difficulty levels, and I'll do a little bit more narration as well that might help you with how to actually tackle questions like this, and hopefully also alleviate some of the pressure. You'll start to see that these are not easier than what you'll see in GAMSAT, it's just that they're probably on the easier to medium end. I've got them all on the resources page, which will be linked below as well, and you can see I rate them on difficulty. I've put these two sets of questions, which will all go into the one, as a medium difficulty, which is kind of down on the lower end of my scale. It kind of goes easy, medium, difficult, very difficult, and then impossible or nightmare, I think I call it. Yeah, so hopefully this helps with breaking down some of the questions. The first set is going to be physics based, and then the second one is going to be chemistry. These are the two that are probably a little bit more content heavy, probably freak people out a little bit more as well. Excuse all the noise in the background if you can hear. There is a really bad storm going on in Melbourne at the moment. This was the time that I had to film, so I'm just going to see what I can do with it and see if I can get some decent audio out of it. Also, if you didn't catch it already on my Instagram post or on the community page as well, Kate Robson and I are to have a chat about all things basically GAMSAT application processes, but also just other stuff as well, what's going on in our lives and that kind of thing. So we're doing a bit of a Q&A. I've posted that up if you want to either reply in a comment, you can send us a message, or you can also go onto like Instagram stories and put it in there. If you've got a question for us, you can submit it there and then we will answer it in the video as well. We're doing it next Friday, the 10th of December, I think it is, if I've got my dates right. And then the video should be out probably sometime soon after that. So if you're interested in getting any questions answered, whether it's to do with your own GAMSAT and application process, or if it's just something weird that you want to learn about either of us or both of us, throw in the question and we will get onto it in the video. All right. So we've got here a cyclist is traveling down a steep hill when a car passenger opens a door in their path and the cyclist collides with the open car door. During collisions such as this, impulse I is the experience of a change in momentum P and is equivalent to the product of exerted force F and the contact time of the collision delta T. And it gives us the formulas there as well. Whenever you see these, it means that they're all equivalent. You could take any two items and match them and make them equal to each other. So that means that we could say that I is equal to delta P. We could also say delta P is equal to M delta V. We can also say M delta V is equal to F delta T. We could also say I is equal to F delta T and every other version of it, right? I think we get the picture. Okay, so if we look at this, then it says the graph below summarizes the change in velocity of the cyclist throughout the duration of their crash. And we've got there, the graph there, if the cyclist and their bicycle have a combined mass of 80 kilos and the value of gravity is taken to be approximately 10 meters per, that should say square seconds. As always, I have my characteristic typos along the way. Should edit these more and more. Question 1, we've got the impulse experienced by the cyclist. So it's numbers, so I'll go straight into formulas. Whenever you see numbers, it usually means you're looking at a graph or a formula, and there's very little like text information, so it is really very much a kind of math skills based question. So we're looking for the impulse. Impulse was I, so we've got a bunch of different ways to calculate it. So we look at what information we've got. So the first one is change in momentum. Momentum is not quoted, but we do have a breakdown of what that means. It's the change in velocity times by the mass. So if momentum is mass times velocity, if you're looking for a change in it, just think, well, what variables can actually change? Mass can't change, so that's going to stay M. Where's the change coming from? Must be a change in velocity. That's how we can kind of logically break down that formula as well. So if we do that, we can go, well, can we work out the mass? Yes, we have that here, 80 kilos. And we also have the change in velocity. Well, they start at 12 meters per second. They're crashing for the course of 0.5 of a second, and they come to a dead halt there. So that would mean that their change in velocity is technically negative. They've lost it, but we're not playing around with signs here. their change in velocity is 12 down to 0, so they've lost 12 meters per second of speed. So that would mean their mass times by, we'll do it in full, 0, final velocity take away initial, and we get 80 times negative 12. Again, the negative is not being shown in the answers, but if we do that fully, negative 960. Keep in mind, if you're worried about the times tables, ignore the 0, 8 times 12 is 96, put the 0 back on, 960, and that would be in kilograms meters per second. And there we go. The next one then says, with what force did the open stationary car door exert on the cyclist? That doesn't make any sense grammatically, I've got to fix that, and their bike. So we use Newton's third law, would suggest, this is a bit of implied knowledge, would suggest that there's equal force applied from either object, so you don't have to overthink it or anything about, well, what was the car doing? Whatever force they exert is the force the door exerts back. So here we've got force in this part of the formula, so we can say, well, if we know the impulse is 960, we can equate that to force times delta t, and the delta t is given in the graph. The crash exists for half a second. So if we do that, that would be 960 is equal to f, make that look a little bit more like a t, f times 0.5, and we can divide the 0.5 across. Dividing by half is equivalent to multiplying by 2, so it becomes 960 times 2, and then that would give us 1920 newtons, just like that. We get option C. So you can see a lot of these maths questions, they're pretty quick. Once you kind of connect the pieces of information to which part of the formula, then you're just plugging them straight in. If the cyclists were instead traveling at a velocity v this time, not 12, and that approximately 20% of the energy of the collision is going to be absorbed by the door, at what speed does the cyclist bounce off of the door? So this is now using the concepts of conservation of energy and the conservations of momentum. So we don't have anything to suggest that the car moves in any way. So we're going to look at the energy side of things. If 20% is absorbed, we have to go, well, where did that energy come from? The cyclist was traveling at 12 meters per, at v meters per second, I should say. So they would have fully kinetic energy. It's the only thing we can consider, which is half mv squared. Now, realistically, that would maybe be given in the question. And I might even go back and edit that. It's maybe a little bit unfair, but it's good to know that going in from a physics perspective. We know what their mass is. That hasn't changed. It's 80. This time we don't know what their velocity is though. So we have 40 v squared is the energy in the system. Now 20% of that is going to be absorbed. So that would mean that we're looking at how much the cyclist maintains. That means that if 20% goes to the door, then the other 80% remains with the cyclist. So if we want to multiply this by 80% or 0.8, the quicker way to do that is times it by 4/5. And that way then we can cancel some stuff off. So 40 and 5 can cancel down to 8 and 1, and it becomes 8 times 4, which is 32v squared, is now the energy that they have. If we let that be equal to a calculation for their energy, we can solve backwards and work out their final velocity. So if this is their final, I'll put vf, so we know what we're solving for. So it's 32v squared is equal to half times 80 times vf squared. So 32v squared is equal to 40 vf squared. We can divide the 40 under. We get 32v squared on 40 is equal to vf squared. And then we can simplify this fraction into 4 over 5, dividing them both by 8. So 4v squared on 5, like that, is equal to vf squared. And so vf, the final velocity, would be the square root of this, which would be square root of 4v squared on 5. And if we simplify that, then we can see that we can go square root of 4, square root of v squared. You can split them all over the square root of 5, which gives us 2v over the square root of 5, like that. And so the only option there is going to be A. Now, in case that was a little bit confusing, I'll just go back for a moment and explain where this bit came from, because that's probably the most important part of this question. So what we're doing is we're working out what is the energy that they have, and then going backwards and pretending like we don't know what that is and going, how would we calculate that? That would be half times mass times their velocity, v final, squared. And it gives us an equation to work with then, all of a sudden. And there we go. So they like to, in physics questions, not necessarily end on numbers because it might be a little bit too easy. They like to rely on having things in terms of a variable to test people's understanding of the maths and also test that you're trusting the process as well. So question 4 then, which of the following is true? Doubling the contact time of the collision will do what? So this one I would take as a proportionality question because we don't have absolute numbers, we have changes. So first of all, I would look at the questions, at the options, because I don't know which variable they're really looking at. So we're changing the contact time, we're doubling the contact time. First one says the force, double the force will be experienced by the cyclist. So if we look at the formula that has those, that was I is equal to F times delta T. So I want to get a connection between force and time. So I'm going to rearrange this. Force is I divided by time. So therefore force is inversely proportional to time. So if I double this, and I put a 2 in place of time, I get half. That would mean that the force would actually halve instead. And that allows me then to immediately work out that the answer must be B. It's not any of the others. Quadruple would be a squared relationship. A double would be a linear relationship and or a direct relationship. And D, double the impulse of the collision. Impulse of a collision is fixed. If it's down to the change in the momentum, the mass is not changing, and the change in velocity is also not changing for this particular incident. So therefore you actually can't change the impulse of a particular collision without changing one of those two variables. All right, so we jump along now, we've got a chemistry question. And again, the point of this is to show that we can use some basic principles of chemistry, but we don't need to know everything in it, right? We rely on the information given, and a lot of chemistry questions are pattern recognition. So we've got polyunsaturated fatty acids, PUFA, are long carbon-based carboxylic acids containing multiple carbon-carbon double bonds along their length. Polyunsaturated fatty acids are commonly found in the phospholipid bilayer of the membrane of many animal and plant cells. The bis-allelic positions of a PUFA are prone to oxidation. So there's a lot of jargon that I'm throwing in there, which involves the removal of hydrogen attached to carbons between two carbon-carbon double bonds, so as to prevent oxidation. Deuterium H2, so an isotope of hydrogen, is substituted in place of hydrogen in all of these bis-allelic positions along the length of PUFA. So we found here the bis-allelic positions, we can see from this, are going to be, and it says here, between two carbon-carbon double bonds. So we've got a carbon-carbon double bond, carbon-carbon double bond. So this carbon position just here must be this bis-allelic position that they're referring to, or that I'm referring to in the question. And so all it's really said is we're just replacing hydrogen with an isotope, H2, but it's going to be represented as the letter D for simplicity, like that. And we've got a whole bunch of examples here. We'll come back to that. So then it says the semi-structural formula of arachidonic acid is. So this one, we don't really need to use a lot of the relationship being presented. We just have to understand what does semi-structural formula mean and where is arachidonic acid. It's just here. So we have to match it. So semi-structural formulas break down the structural formulas shown in the diagram, and they kind of condense it down to say whenever there are repeating units of say CH2 or so on, you put it in brackets and then write how many there are. And it kind of squashes it down a little bit. So the first thing is, if I look at all of them, they all start with a CH3 end except for D. So that is on this end, not on this end. And so now I'm going to count it. So there would have to be a CH3. So A, B, and C are all looking good. Next piece then is I've got 1, 2, 3, 4 CH2s before I hit a double bond. So this one says CH2, 4, just there. I might zoom this in a little bit. So you can see there, this one's good, but now B is out. D's already out from the start because I had CH2, no CH3. So then the next thing is now I'd start looking at, well, what's the difference between A and C? So here's the difference. The next bit says CH, CH, CH2 5 times. A says only 4 times. So I'm going to go back to arachidonic, find what that's looking at. So this would be my CH, this would be my CH, and this would be my CH2. And I can see that right there is repeating itself here and repeating itself here again, like that, right? And so that would mean in this particular case that we've got 3 of them. So that's actually a slight typo. I'll have to fix that. That'll already be fixed, though. Don't worry about that. That we've got 3 of those. And then it has a CH and a CH at the end there as well. So if we come back over to here, there we go. I've just fixed that now. Then that one has CH3 and so, or CH2 3 times. And so now I know this bit's correct. And then it has CH, CH, CH2 3 times. So then I can see there's my CH, CH, and then CH2, CH2, CH2. So that's my CH2 3 times, and then a carboxylic end as well. So A matches up the most closely, and so therefore the answer will be A, like that. Now in terms of theory that we are using there, because you may have missed a trick along the way, how did I know that these were CH and these were CH2, for example? Comes down to the number of bonds that carbon can have, which is a key thing in organic chemistry, and that is it can only ever have 4 bonds. In fact, it should have 4 bonds. So if we look at this carbon here, it's already got 1, 2, 3, so it's only got 1 more space left for a hydrogen, and that's how I know it's just a CH, versus this carbon here has 1, 2 to the chain, so it needs 2 more spaces filled up by hydrogen, so that would be a CH2, and the same concept with all of these as well. I know they're CH2s because if, say, this carbon, it's got a bond there, so it needs 2 more bonds to fill up its 4, and there we go. All right, so then the next one we have is how many grams of deuterium would be required to fully substitute, slight typo, fully substitute and protect 3 mole of linoleic acid. So it was referring to the deuterium substitution as a way of preventing oxidation or perioxidation. And we're looking for how many grams of deuterium would be needed to protect 3 mole of linoleic. So let's go find linoleic first. Here it is here with its protection on there. It needs 2 deuterium per molecule. So we always want to work in moles first and then convert out to mass at the end in chemistry. So if we have 3 mole of the acid, then we have 2 mole of deuterium per mole. So the number of deuterium to the number of acid as a ratio is 2 to 1. So therefore, if we have 3 mole of acid, we should need 6 mole of deuterium. The final thing then is we're told deuterium is H2, and that has a mass number of 2. So the mass, this is using a bit of stoichiometry, is number of moles multiplied by molar mass of the compound. If we have 6 mole and it's got a molar mass of 2, that gives us 12 grams of deuterium is required. And there we go. So in that case, then we would need 12. And there we go, there's 12 grams. Which of the following is true? So we've got a bunch of different statements. Here I would use test and check method, and we'll just go through each of them and check their truthfulness. So docosahexaenoic acid, they're going to be tongue twisters, requires less deuterium per gram than icosapentaenoic acid. So we're going to go and find those first and see what is going on with them. Docosahexaenoic, so that's down here, and we're comparing that to icosapentaenoic, require less deuterium. So we can see you get 1 deuterium for every, or deuterium, I don't even know if I'm saying that right, for every hydrogen. And so we can see this actually requires more, not less, because it's got more hydrogens, therefore needing to be substituted. So that one is out, it's the less bit that's wrong. Then we've got linoleic and arachidonic require equal amounts of deuterium per gram of acid. So this one's per gram. So if we look at that, linoleic first, here it is over here, and arachidonic down here. So looking at their lengths, if we count up, the carbon is going to be the thing that affects the mass the most. Whenever we want to convert to mole, we have to know the molar mass. So if I look at the carbon chain, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If I then look at arachidonic, it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So arachidonic has a much, much heavier mass. So per gram, you're going to have far fewer mole of arachidonic. So linoleic requiring equal amounts, not only does it have a different ratio of hydrogens, but it's also got a completely different mass number. So the number of moles of linoleic is going to be significantly smaller, and it also requires less deuterium per mole. So it definitely is not going to be equal without doing any more of the maths. D8 acid has equal molar mass to D6. So if I look at those two, again, we can do that thing of counting the carbon chain length first. And if we count them up, you'll find that there's exactly 20 carbons in this one, and there's exactly 20 carbons in this. Now you might look at that and go, hang on a second, this one has 6 deuterium, and this has 8 of them, which is where the names kind of come from. And deuterium is heavier than hydrogen. But the trick to it is that you're also getting an extra double bond out of this. And what does a double bond do? It removes a couple of hydrogen. So if you're getting a hydrogen just here, a double bond just here, then you're removing one hydrogen, and you're removing one hydrogen from the other carbon. Hydrogen has a mass of 1, so you're losing a total mass of 2 and replacing it with a couple of deuteriums, which are 1 unit heavier each. So you're losing 2, but then gaining an extra 2 in mass as well, right? It's equivalent to remove 2 like this from either end, and then replace hydrogens with deuteriums. So you're removing another 2 hydrogens, and then you're replacing them with 2 lots of deuterium, which have a mass of 2, and then that just means you get -4 plus 4, and it goes back to 0. So you're not actually changing the mass at all. Everything else is the same, and so therefore C is actually correct. It's a bit of a trick question. Then D2 linoleic is more prone to peroxidation than linoleic acid. That would be wrong, because D2 has already been protected. It would be less prone now, because that was the goal of it. So that's just kind of thrown in. And then question 4, for DX PUFAs, where X represents the number of deuterium atoms substituted on the bis acylic positions. Lots of jargon again, but you can kind of skip past a lot of it. 2 of the fatty acids, compound A and compound B now, have equal carbon chain lengths, but varying degrees of unsaturation. Compound A contains 3 carbon-carbon double bonds, whereas compound B contains 5. And then for these 2, which of the following would be true? So first of all, the value of X will be larger for compound A. No, because compound A had 3 carbon-carbon double bonds, and if we look at the patterns in everything we're given, every time for every double bond added, there was another 2 deuteriums. And so compound A has less double bonds, and so therefore it'll have 6 deuteriums, right, for 3 carbon double bonds. This one would have 5 double bonds, therefore 10 deuteriums. So first of all, X will definitely be smaller for compound A. The next thing then is the molar mass of compound A will be less than that of compound B. What we can do here is use the finding from the previous question. Because they had equal carbon chain lengths, adding double bonds and replacing hydrogens with deuterium didn't actually affect the mass number at all, because what you were removing, you were then adding in the process of adding a heavier isotope. And so therefore, if they've got the same carbon chain length, just different numbers of double bonds and deuterium, then they should have equal mass. And that would give us option C. It's like that. So you can see that there's very little chemistry actually being used. Being familiar with it is going to obviously speed up your processing, but the only thing that we actually used there from outside knowledge would have been the concept of carbon having a valence of 4 and having 4 bonds, and knowing what that means in relation to double bonds in carbon structure. Everything else, and the stoichiometric calculation as well, the mass is number of moles times molar mass. Outside of that, everything else is provided, and you're just following a pattern based on what is presented to you. You wouldn't be expected to know all of these different acids or anything like that. Truthfully, I would look at this stuff and go, I'm not familiar with it, but I'll just follow along, no problem. You're just looking for patterns using the information that is presented to you to then reason with the questions. And there we go. Cool. So hopefully that's all been helpful. Hopefully this one's been nice and rapid, quick, a little bit more broken down, a little bit more accessible in terms of the question difficulties. And I'll try to mix it up and do some of these intermediate ones as well as still some of the more difficult ones for people that are a little bit further on in their Section 3 study. As always, leave me some feedback, leave me a comment, let me know what you think, and I will see you guys in the next one.